computer generation in C. Computers have revolutionized the world, becoming an integral part of our daily lives. At the heart of this technological revolution lies the programming language C, a powerful and versatile tool that has played a pivotal role in the development of modern computing. In this introduction, we will explore the fascinating process of computer generation using the C programming language, delving into its history, fundamental concepts, and practical applications. Now, let us know the history of computer development. Early computers. The history of computer development can be traced back to 1930s and 1940s, when pioneering scientists and engineers began exploring the concept of programmable machine. The first fully electronic general-purpose computer, the ENIAC, was developed in 1946 at the University of Pennsylvania. These early computers were massive, room-sized machines that required a significant power and cooling systems, and were primarily used for the scientific and military applications. The rise of mainframes. In 1950s and 1960s, the computer industry saw the emergence of mainframe computers, which were large, powerful, and expensive machines primarily used by the large organizations such as governments, universities, and corporations. These mainframes were often housed in dedicated computer rooms and required specialized personnel to operate and maintain them. The development of high-level programming languages such as Fortran and COBOL helped the expand of the use of mainframes in a variety of applications. The personal computer revolution in 1970s and 1980s marked a significant shift in the computer industry. With the advent of the personal computer PC, the introduction of the Apple and the IBM PC in the late 1970s or early 1980s made computers more accessible to individuals and small businesses. These PCs were similar, more affordable, and easier to use, having the way of widespread adoption of computers in home and offices. Fundamental of computer architecture. Computer architecture is a fundamental design and structure of a computer system, defining the key components and how they interact to process data, execute programs. At the core of a computer's architecture is the central processing unit, which fetches instructions from memory, decodes them, and orchestrates the flow of data between various components to carry out those instructions. The CPU is supported by other essential architectural elements such as memory for storing data and programs, input and output devices for interacting with the external world, and a system bus for coordinating the transfer of information between components. The memory hierarchy, which includes fast but expensive cache memory as well as larger, slower main memory, plays a crucial role in optimizing performance by providing the CPU with the data it needs when it needs it. Peripheral devices such as keyboards, displays, and storage drives are also an integral part of a computer's architecture, connected to the system through specialized interfaces and controllers. The design of these interfaces, as well as the overall organization and coordination of the various components, are all full fundamental aspects of computer architecture that enables the seamless functioning of a modern computer system. Data representation in C. In the world of computer programming, the efficient representation and manipulation of data is a fundamental aspect of any programming language, including C. C, as a low-level language, provides developers with a deep understanding and control over how data is stored and processed within the computer's memory. from the basic data types like integers, floating point, numbers, and characters to more complex structures like arrays and structures. C offers a versatile and a powerful set of tools for representing and working with data. One of the key principles in C is the concept of bits and bytes. The building blocks of digital information, bits, which can hold a value of either 0 or 1, are combined to represent various data types. Bytes, consisting of 8 bits, serve as the basic unit of memory storage. C allows programmers to work with these fundamental units, enabling precise control over how a data is stored and manipulated in computer's memory. Beyond the basic data type, C also supports more complex data structures such as arrays, structures. Array follows storage and manipulation of multiple values of the same data type, while structures enable the grouping of different data types into a single cohesive unit. These data structures are essential for organizing and processing complex data in application ranging from scientific computing to game development. Memory management in C. Memory management is a crucial aspect of C programming as it follows developers to dynamically allocate, store, and deallocate memory resources as needed. Process begins with dynamic memory allocation where the programmer uses functions like malloc and calloc to request memory from the operating system. This allocated memory must be then carefully managed, ensuring that it is efficiently utilized and that memory leaks are avoided. Finally, when the memory is no longer needed, the developer must explicitly free the resource using the free function, preventing memory fragmentation and ensuring the program's stability. Proper memory management in C requires a deep understanding of language memory, model of the underlying hardware architecture. Developers must be mindful of factors such as memory alignment, pointer, arithmetic, and the behavior of the memory allocator. By mastering these concepts, programmers can write efficient and robust C code that effectively manages the available memory resources, optimizing the program's performance and reliability. Input and output operations in C. One of the fundamental aspects of programming in C is input and output operations. In C, we can perform various types of input-output operations to interact with the user, read and write files, and communicate with external devices. The standard input-output library in C, known as Studio.h, provides a wide range of functions for these purposes. To take input from the user and can use the scanf function, which allows you to read data of different data types such as integers, floating point, numbers, and strings. Similarly, the printf function is used to output data to the console and you can format the output using format specifiers. C also provides low-level input-output functions like read, write to interact directly with the operating system's file system. File input-output is another important aspect of C programming. You can use functions like for open, fread, and fwrite to open, read, and write files, respectively. C also supports binary input operations, which can be useful for working with data in a more efficient and compact format. Control structures and algorithms in C. Conditional statements. In conditional statements like if else and switch provide this ability to execute different code blocks based on specific conditions. These structures allow you to make decisions and control the flow of your program, enabling more complex and intelligent behavior. Mastering conditional logic is essential for writing robust and adaptable C code. Loops. Loop in C is such as for, while, and do while allow you to respectively execute a block of code. This is particularly useful for tasks that involves repetitions like performing calculations on a set of data or implementing algorithms that require multiple steps. Functions and algorithms. Functions in C are self-contained code blocks that encapsulate specific functionality. They allow you to break down complex problems into smaller, more manageable piece programming code, views, and maintainability. Algorithms, on the other hand, are a step-by-step procedure for solving problems. File handling in C. File basics. In C programming, file handling is an essential skill for working with data storage and retrieval. Files allow you to persist data beyond the runtime of your program, enabling you to save and load information as needed. The basic file operations in C include opening, reading, writing, and closing files. Opening and closing files. To work with in C, you first need to open them using the fopen function, which takes the file path and mode as R for reading, W for writing, or A for appending as arguments. Once you're done with a file, you should close it using the fclose function to ensure that the data is properly written and resources are freed. Reading and writing files. After opening file, you can use functions like fread and fwrite to read from the write to the file. These functions allow you to transfer data between file and your program's memory. Error handling. File handling in C requires careful error checking to ensure that your program can handle unexpected situations gracefully. Functions like foff, ferror, and perror can help you detect and respond to errors that may occur during file operations such as file not found, insufficient permissions, or disk full of errors. Debugging and error handling in C. Debugging tools and techniques. In debugging is a crucial aspect of C programming as it helps identify and resolve errors that can arise during code execution. C provides a range of debugging tools such as GNU Debugger, which allows developers to step through their code, examine various values, variable values, and pinpoint the source of issues. Additionally, techniques like print statements, assertions, and error logic can be used to help allocate and diagnose problems within the codebase. Common C errors and their causes. C is a low-level language that gives programmers a high degree of control, but this also means that it is susceptible to various types of errors. Common C errors include segmentation faults, invalid memory location, buffer overflow, and underlying behavior and undefined behavior. Variables. Understanding the root causes of these errors is essential for effective debugging and error handling. Error handling strategies. Effective error handling is a C involves combination of proactive measures and reactive response. Proactive measures include input validation, boundary checks, and defensive programming practices to prevent errors from occurring in the first place. Debugging workflows and best practices. Debugging in C often follows a systematic workflow starting with reproducing the issue, gathering relevant information, and then using debugging tools to step through the code and identify the root cause. Now let us come to conclusion and future prospects. As we have explored the fundamental aspects of computer generation in C, it is clear that this programming language has played a wide pivotal role in shaping the technological landscape. From data representation to memory management and input-output operations, C has provided a solid foundation for building robust and efficient computer systems. Looking towards the future, the continued advancement in computing power, software engineering, and emerging technologies such as artificial intelligence and quantum computing will undoubtedly expand the possibilities of what we can achieve through C programming. The versatility and low-level control offered by C will ensure its ongoing relevance in the development of mission-critical systems, embedded devices, and high-performance applications. As new challenges arise, the availability to manipulate hardware directly and optimize code for speed and efficiency will remain invaluable. Furthermore, the principles and problem-solving skills honed through C programming will continue to valuable assets for the next generation of software engineers and computer scientists. Thank you for watching the video.